Hi guys, this is Mrs. Gassler, and in this video we're going to be talking about the modern model of the atom and electron configurations. What you're going to need for this is some Cornell paper. Your periodic table is useful, and this handout that is the tiny periodic tables with the patterns labeled on it. It's got some on both sides, and you'll need one of those to be able to color a little bit, or you can use another periodic table. It's totally up to you, I suppose. Okay, so I've got my Cornell paper partially filled out to save a little time on the video, so if you need to pause it to get something written down, please do so. Okay, so name, date, class period go here. We're talking about objective 5.6, the modern model of the atom, and we're going to talk a little bit about what an electron configuration is. There we go. Okay, two essential questions. What does the modern model of the atom look like, and what is an electron configuration, and why do we write it? Okay, so in order to understand the modern model of the atom, we're going to look at some patterns in the periodic table that we noticed. So we've got Bohr, he's got those energy levels, and we're going to put some electrons on there. First, we're going to look at the first column. The first column here is this. It's also called a group. We're going to look at hydrogen, lithium, sodium, and then we can talk about what those other ones are going to be like. So let's go ahead and do that. So there's one proton in hydrogen, which means there's one electron on that first energy level. Lithium has 3 protons, so it has 3 electrons, 1, 2, and then one more electron, but this first one is full, so that goes up 1. Sodium has 11 protons, so 11 electrons, 2 on the first energy level, 8 on the second energy level, make us have 10 electrons on that sodium atom, and then that last 11th electron goes on the outermost ring. So what do you think would be true for potassium? If you think that there will be one more energy level and then one more electron on the outside like that one, you would be right, and that is the pattern that we see on our periodic table. So in a column, we see that each has one electron on the outermost level. And it'll come in handy later on one of the other objectives, but that's called the valence level. So there's one valence electron. And as you go down, we add an energy level. So potassium here is the next one down. We would expect it to have a 4th energy level and 1 electron on the outside. So that's the going down the periodic table. If we go across the periodic table, and what we're going to do is we're going to look at the second row because there's just not a lot on the first row, so we're going to look at lithium, beryllium, boron, and carbon. Well, let's see what patterns we see there. We already drew lithium, 2 protons, 1 electron. Beryllium has 4 protons, 2 protons here, 1 on the outer level. I may have said 1 electron, I'm sorry. This one's got 2 now. Boron has 2 in the middle, or on the first level, and 1, 2, 3, because it has 5 protons. Carbon has 6, so it has 2 here, and then 1, 2, 3, 4. So what we see as we go across the periodic table is a little bit different. So what they have in common, each has 2 energy levels used. So despite the fact that we jumped over this big blank space in the middle, it's still the second energy level. Here is still the 3rd energy level. So we have those energy levels that are being used. As we go down the row, though, or as we go across, as you go across, what we changed was, instead of energy levels, which I forgot to write there, we added 1 electron. So we might expect then that nitrogen is next, so instead of having 4 on that outer level, it probably has 5 on that outer level. So that's the pattern we see there. All right, so the last thing I wrote on this side of the paper was that we're going to look at those small periodic tables for patterns. I've already colored mine, and you're going to color yours to match. This is what mine looks like. Now the pattern that I've looked at here is the last energy level that's filled. It's not necessarily the outermost, which we'll talk about later, but this is the last energy level filled. And so these guys have the first energy level. We looked at this one, it's the second energy level, and here's the 3rd energy level, but you might notice that there's some 3s right here, and that the 4s dip down, and that the 5s dip down, and the 6, and then this, which would belong right here, would mean that my 4s would dip way down and go back up. And that's exactly what happens. So these are the patterns that we see on the periodic table. So stop the video and color your periodic table to match. And when you're ready, flip over to the other side of your paper. All right, so then the next thing we need to talk about is why those rows are not straight across. So some other people noticed that those rows weren't straight across, and this guy named Schrodinger asked the question, how does energy change as more electrons are removed? So here's my atom. If I pull electrons off, it gets harder the more electrons I take off, and as a result of that, what's changing? So he wanted to look at exactly what was happening, and this is what he expected. He expected, so let's take a big atom, we're removing these electrons. It's going to take a little more, a little more, a little more, a little more. They're on another level, a more inner level, so we're working our way in. So it's going to even be more energy. And then he thought, oh, second, even more energy, and first, even more. And what he found was something entirely different. I should have drawn, whatever. Okay, so he found that in the fourth energy level, some of them were here, some were here, some were here, and some were here. And then some of the threes were here and here and here, and some of the twos were like here and here, and the ones were all together. And so what we see here, and this may not be accurate, this one does jump up above the fours, but the threes and twos don't. What we see here is that the levels are kind of split up. And it didn't matter what atom he tried, this was the case. So the conclusion that he came to was that energy levels have sublevels. So these sublevels that the electrons can be on, he decided he would call those orbitals. Now, the definition of an orbital is that it is a shape or a location where electrons could be. And after more research and a lot of other things, they were able to determine some more stuff about these electrons. This is actually getting into more of the physics behind it, but these are some pictures of those shapes of the orbital. So some of them look like flowers. This one's my favorite here. Actually, I like that one a lot too. Okay, so this one over here, they all have at least one split, and they called that first split S. And then here we have a second split that we call P, the second sublevel. And there's different shapes that these can have. In fact, you can have two of this one, but one of them would be oriented this way, so coming in and out of the page. And each one of these can hold 2 electrons. So S can hold 2, P can hold 2 here and 2 in each of those, so it can hold 6. This one they called D, not F. D, this one can hold, has 2, and this one has 2 because we orient it this way. This one is symmetrical around. It looks kind of like that when it's solid. And so this can hold 2, 4, 6, 8, 10 electrons here. And then this last one is called F. I remember the order by remembering speed, fast. I don't know why. Speed, fast is what comes to mind. So we have S, P, D, and F. S, P, D, F. All right, so this matches what Bohr talks about in his energy levels. So we're gonna compare that. So we're gonna write the energy level here. This is a chart I made. Feel free to make one. It looks like that. We're gonna write the orbitals here, the number of electrons here, and then the total number of electrons here. So we've got 1, 2, 3, 4 energy levels we're gonna look at. Bohr said that we had to have a certain number of electrons, and we know that it happens to be 2, 8, 18, and 32, so we'll see if those match or not. All right, so in the first energy level you have S, second you have P and D, nope, S and P. In the third you have S, P, and D. We always have this S level, P level starts in level 2, D starts in 3, and then we have S, P, D, F. There are more energy levels and more sub levels. Those orbitals are there too, but we actually don't need any more than this because we don't have any atoms with more electrons than that, but that's okay. So we can fit 2 in S, which means we'll have 2 total electrons. Check. S can hold 2, P can hold 6, so that's a total of 8. Check. S can hold 2, P can hold 6, D can hold 10, because remember we've got 2, 4, 6, 8, 10 in each of those. 10 plus 6 plus 2 is in fact 18, so we're matching there too. S can hold 2, P can hold 6, D can hold 10, and F, we've got times 2 of this, 2 of this, and 2 of this. So we've got 2, 4, 6, 8, 10, 12, 14. So there's 14 electrons there. Add all that up, 4, 6, 2, gives you 2, carry the 1, 32. Hey, look at that. It does work out. So Bohr's model of the atom, turns out, matches what Schrodinger found also. Okay, so one more periodic table. It says see small periodic table for patterns in orbitals. So this is what we see. This is looking at the last orbital filled. So electrons come in and they fill these things. What's the last orbital that gets filled? Because remember, in that graph here, they did some overlapping. Well, it turns out it looks like this. If we move helium over here, we have this nice, pretty S block. These guys over here are the p block. They all end in the p orbital. These guys here are in the d block, and here is the f block. Remember that the f block would be right here if it were up in the periodic table. It's actually really cool that it works out this way. Okay, so that's how these things go together. Now, oh no, I ran out of room. Electron configurations are just a way to write where the electrons are in each of these orbitals, and it would look like this: 1s2, 2s2, 2p6, 3s2, where this tells you the level, this tells you how many electrons are there, and this tells you the sublevel. But we'll talk more about that in the next video, how to write an electron configuration. Thanks for watching.